I'll go ahead and get started. So this is an embryo going under morphogenesis. So it's basically changing shape in, this is obviously sped up, but it's a rather incredible process, which I didn't really know about or hadn't looked closely at until this project. And this is another 3D version of this. And I think the coolest part to me is looking at all the cells moving around as this thing goes from a sphere into, I think it's turning into a little fish, or maybe a little salamander. It has little legs going on there too. So this process is pretty incredible, right? I think we can agree on that. And the thing we wanted to ask was, well, what would happen if we could do a synthetic variant of this? And so the question is, well, how do you actually make that into a real robot? So can you do something like this in a real robot? And what's kind of the basic mechanism? So we wanted to ask, well, what is going on to enable this type of shape change, this kind of melting behavior? If we look at an animation of cells as they're undergoing this process of morphogenesis, and if we look closely at them, this is the kind of key behavior. If you notice it, and I'll play this again in a minute, but the cells are actually changing order, right? So their topology is changing. And so cells can move with respect to one another. And they can kind of, by moving with respect to each other, you can change the overall shape of. So this is what we kind of identified the key in both biology and actually these Hollywood interpretations of it is rearrangement. So if you can rearrange your cells, you can do some interesting things. And more specifically, you're rearranging in tight packed situations. So it's not like quadrotors, flying in formation. We're looking at things that are tight packed, and so they're making a kind of a cohesive material. And then it's not. Another kind of key to it is it's happening throughout the material, right? It's not just around the surface or something like this. And so this is kind of what we identified as our target. Was can we do this rearrangement, tight packed, and throughout the collective? All right, and that's what today's talk is going to be mostly about. And it's always good to look at what other people have done so far. So people have done collective robots before that they can change shape, that have units and can move around. So we'll just look at a couple of them. So this is from Mark Yim, his modular robot system. So they can drive around, they can connect to each other, and they can disconnect and change shape of this system. But you notice that any motion of one of these things requires it to basically disconnect and drive around. And so you get motion around the surface of the thing, right, around the perimeters, how they can change. This is a recent paper in Science Robotics. Jaeger, and actually Sminko was on this paper. Yeah. Mark's former postdoc. Yeah. And so, but a similar thing where, again, they're able to move around the perimeter. And so we get rearrangement. We're not be able to do it throughout. And then this is one that probably people have seen. This is kilobots, which I feel sorry for the grad students who were involved in this project. 1,000 robots is a lot of robots to make. But again, we see this same behavior where we can do really cool shape change, but it's limited to perimeter motions, right? So we're not actually moving anything in the bulk of it. So this is kind of what we're looking at to talk about today. Is what I'm claiming is that this is kind of a key step to realize these kind of programmable matter things that we see in tissue or science fiction, is to do what people have done with rearrangements, but actually do them in a tight packed situation where we're getting motion throughout the material. And it turns out no one's done it because it's hard. It's much easier to drive around the outside than it is to rearrange things that are tightly packed together. So a little outline for how I'm going to break this down. We'll talk about the design of the robots first. So what did we learn from the embryo, and then how do we implement it into a robot? Once we built the robot, learning about how it behaved. This was pretty interesting. Once you do multi-robot things, unlike when you kind of have one robot and you program it and it basically does hopefully what you tell it to do, when we have multi-robots, you tell each one to do something, and then you put them all together, and something happens, right? And so that's been very fun. It's a little more like biology, where you observe, as you change different parameters, what happens to the collective. And then finally, I'll end with some demos of things these our collective can do, which, just as a warning, is not going to be Terminator. So keep your expectations low. And then I want to recognize the team here. So Matt Devlin is my PhD student who has put in a ton of work into this. So he's the main driving force in all of this. Uche Campas is the mechanobiologist who's been helping us to understand the cells and how they work and all the forces and everything going on. And then this was his postdoc, Songwoo, who's now a professor at the PFL. So it's a international team, so it's always challenging to find times when we can all meet. But let's start with the design. So this is this goal here, right? There's a rearrangement and tight packed and throughout. And the question is, how do we do that in a robotic system? And we're going to start with first just this rearrangement piece. So if we look more closely at that simulation of how the cells are interacting with each other, let's zoom into 4 of those and watch how they move. So you've got 2 cells here and 2 cells here. And the most basic way we could rearrange, or a basic way we can rearrange the topology of this, so basically these are neighbors and these are not neighbors, and we're going to change it so that these come together and those split apart, right? So you can watch that happen. And that's called the T1 transition in biology, or in topology more generally. So it's this very basic transition where 1 and 4 come together, 2 and 3 split apart. It's also known as intercalation, because basically these cells here are intercalating like this, and we are essentially going to elongate the tissue along this axis as we get the things coming together like that. So this is this basic functionality that underpins a lot of biological shape change and strength change. And so, so we've identified this T1, and so then how do we recreate it in robots? And so there's kind of 3 different things I'm going to talk about for recreating this T1. And first we're going to look at how do we actually apply the forces necessary to create a T1 transition. So the first thing we noticed was that we got 1 and 4 here, and somehow there must be some force that pulls 1 towards 4, right? Because they're apart and then they come together. So we said, okay, let's look at ways to do that. And I'm going to show some of the very bad ideas we had, because I think that's fun to show. When often you go to a talk and you just see the final product and you say, wow, how'd they come with that? But there's lots of things like this that didn't work first. So these were all a bunch of little cells we made. And the idea was we'd have on each cell these little arms that would reach out, and then they would pull, and they'd reciprocate like this to try to pull the other cells towards it. So I will play that. Kind of working, but not really. So it just kind of wiggles back and forth, and we don't really get any net motion. So this is something like 4 years ago, and I'll just stop it there because it does about the same thing. The next thing we thought of was, okay, well, what if we attach the 2 cells that we care about with some kind of, here I think they're badge retractors, but some active tension mechanism that would pull the 2 cells together. So you could, they would split apart like this. You put them together, and then if you pulled hard enough in that cable, you can pull 2 and 2 together and split 1 and 1 apart. This is great, but you can only kind of do 1 motion, right? You're kind of stuck, and after you do your 1 motion, you could pull 1 back together, but you can't really do random, arbitrary rearrangements in your system. So that wasn't a great idea either. So we looked a little more at what's going on as you do this intercalation, and so this is a similar drawing, but now we have A and C coming together as B and D are splitting apart. And we read some old papers that were explaining how some of this worked, and partly it's due to this flow of lipids in the membrane of the cells. So there's actually this recirculation of the membrane that goes this way and then comes in. And if any of you have done Vine robot things, you start thinking, well, that looks a lot like a water wiggly or a Vine robot. So I started thinking, oh, all my projects are actually going to be the same. And we tried this, and it didn't work. So I'll spare you. This is not a Vine robot talk. So we looked at it again, and if you look really close right in here, we said, okay, so A and C are coming together, B and D are coming apart. What are the forces or the flows that are happening at that junction? And so basically you're getting, on C for instance, you're seeing C's kind of coming in, whereas D and B, the membrane is going away, and the same with A. A is kind of coming in like this. And so because if you look at right here, there's more, it's hard to see, but as you go from this picture to that picture, there's more membrane here than there is here. So there's a net flow in, and there's a net flow out on B and D. You said, okay, so how do we replicate this? So we started thinking, well, maybe it's about like surface flows or tangential forces acting along the surface. They can essentially make a flow of material right along the surface. So here we've got a rubber band driven by a motor along some pulleys on the outside to essentially get a flow of material around the outside of the robot. So this is an early version, and you can kind of see things moving around. You can see the belts moving, and it was kind of working, and then the white smoke of not goodness. So this didn't really work in the end. The belts were a little bit of a hassle to work with, and not... They had their own problems, which I won't go into now, but we started realizing, well, maybe we can just drive gears along the surface. And so the gear could actually be essentially like, if you think, well, the gear in the inside is not doing anything, on the outside is essentially creating this tangential force or a shear flow. So this is an early version of this, and this is driven by one motor, and they're all moving together. Now, which direction do they need to move? It's a little bit tricky because you need them basically running in opposite directions to create these convergent flows. So this one will be coming in, and this one will be coming in this way, which kind of pulls the flow this way. On this side, there's a divergent flow. So you have two convergent flows, two divergent flows. I'll play that again. So right, there's a convergent flow at the bottom and a divergent flow on the outside. And so when you start putting these together, you get these flows starting to work together. The 4 kind of worked, but you can see there's kind of some big dead zones in there, and so it works better actually with 8. And at 8, and you could keep going with this, right? You could have a million of these, and you would essentially have perfect control along the surface. Turns out 8's enough to approximate surface flows of a cell. And so this is just showing how we can control them all to move around. And at this point, we decided just to give everyone its own motor, and that allowed us just a lot more control than trying to do a somewhat complex linkage in there, or a gear train. Also has the advantage of you can hot swap things in and out when they break, which is helpful when you're building a lot of robots. And so that was essentially the design that we stuck with in the end. We moved the gears a little bit further back so that they're barely going out past this edge of the robot, and that allows us to get this basically just a tangential force along the surface. And then we made it blue and gold for Santa Barbara colors. And that was what we did for the forces, right? So that was the first main design challenge. The second part to create T1 transition is adhesion. These cells need to stick together. That's pretty straightforward. Magnets, many people use magnets for these, right? So there's just this video again where you see the cells are essentially stuck together. Magnets are a very convenient way to do this, so we did that as well. We thought a little bit about how to design our magnets, in that if you start with this red curve, which is just magnets kind of embedded in the robot, and let's say we need some force of about 12 newtons or so. If you look at just putting a big magnet inside, you have this curve. But if we don't want the force to be too far once they've come apart, because you want to be able to rearrange somewhat easily. And so if instead you use a smaller magnet, you can cheat, but you put it right at the surface, so you actually get that initial contact touching. You can get the same force, but you can get a quicker decay, right? Because you have a smaller magnet closer. So we chose that medium magnet for our magnets, and then we want them any two robots to touch another robot and connect. And so the magnets are not glued in place; they're floating in this little holder, and so the magnets can just rotate around to any orientation they need to match with the nearest neighbor. And then the third part for the design of the robot was trying to polarize them. So in the sense that if I'm trying to tell a tissue to elongate in a certain direction, it needs to know what that direction is, and all the cells need to know that direction. All right, so if we have this example again, A and C need to know that they're supposed to go this way, and B and D need to know they're going to go this way for the thing to elongate in that direction. So we need to communicate with our cells in some way. So one of our first ideas was a really bright light on one end of a little arena, and then we would have some photodiodes. You can see them hanging off the end of the circuit boards here. And I'll just play that. I mean, it sort of works. There's kind of a downside. You can see it, is that you get shadowing, right? So it worked great for the first two ones, but then this one's getting shadowed by the other ones, and so that wasn't the best solution. We then went to this idea where the lights are above and swiping across the... so instead of a spatial control, this is more of a temporal control, as when it went across, you would look at your sensors, and if it got lit here before there, then you know which direction was the direction you wanted to go in. So this was kind of okay, but it kind of made us feel like we're going to get sick or something. So this wasn't the best solution. It had some problems in implementation. So then we thought about, well, what if we just use polarized light? Because you can polarize light and essentially give a direction to it. And so this is a demo of that. So what we've done here is, this is the circuit board, and then it has 8 photodiodes. You can see them, the little squares. And then on top of each of those is a polarized film, and they're each oriented radially, so pointing in towards the center. And now you're looking through a second polarized film right now. The camera has a second polarized film on it, which is what the light is also shining through. And so as I rotate this device, you can see that black is always here, right? No matter the orientation of the device, black is always on the side, because it's at that point that it's cross-polarized and it gets dark. And so by doing this, no matter the orientation of the physical robot, I can always have it know which way is north, or whatever you want to call it. Right? So then, and I can just have a bunch of robots randomly aligned, throw them in an arena that it's lit by this polarized light, and they always know which way is which. So we put it all together, and this is our beautiful little robots. So there's a little custom circuit board on top, a bunch of these little cheapest motors we could find on Amazon here. There's the batteries, the gears, and a couple of them touching together, and here's the sensors you can see there. And so then the question is, can we do a T1 transition with all that stuff? And so that's what this looks like. So here's 4 of them set up in that initial configuration. We shine the light polarized this way, it goes that way. We put them back to neutral, then we put it this way, and then they can go up that way. So we have a nice control over this with 4 cells to be able to do the T1 transition pretty robustly. And you can also note, it's kind of cool to see here, these cells were not placed in any particular orientation, right? This one has the blue board this way, this one has it this way, this one has it this way. So you can just throw them in there, and then once you flash the light on them, they change the drive pattern of their gears to essentially all become oriented in the same direction, right? So they're not physically oriented the same way, but they can just reorient their gears, and then they're functionally oriented in the same direction. Cool. So that's the design of the robots. So that's what they look like. That's how we came to the design. And then the next question is, what controls those motions, right? So when we want to have these transitions, how do we control it, and what are the parameters that control it? So we did our T1 transition, and then we're looking at parameters, and we're going to start with shape change. So the 2 things we're interested in generally are shape change, so controlling the general shape of it, but then also strength change. So kind of like the melting of the terminator. When you apply some load to it, can you soften it? And so these are the parameters that we looked at for how does the robot change, or how can we change the shape or the strength of the collective. And so this is the signal that we're sending to the gears. And so each motor gets a signal that has some average intensity or force, and then we have some fluctuations around that average force. And this is something we find in cells, that they fluctuate their forces. They don't just give a constant tension to them. And so one thing we were curious about is, well, what's the effect of these fluctuations? And maybe we could learn a little something about why it's helpful to fluctuate as opposed to just drive with a constant force. So those are 2 parameters we're going to change. And so these are the first set of tests. This is just with that intercalation. So it's just the 4 cells doing this motion. And so the first test is we just vary, this is the average force. So you vary the average force. And as you increase it slowly, you basically get no motion, no motion, no motion. Then you get to this threshold. And then all of a sudden you're going to move. And then beyond that, you basically always move if you have an intensity high enough. So that's with changing the average force. And then you see a similar thing when you change the average fluctuation. So the fluctuation amplitude. So you hold some force. And if you're not fluctuating at all, you actually get no motion. And then as you get more and more fluctuation, eventually you get the same threshold. So you're going to go from no motion to this full motion, crossing a pretty steep threshold like this. All right, so now this is where it becomes interactive to make sure you're still awake. If we have these 2 plots, so this is what happens as I vary F, the average force. This is what happens as I vary the amplitude of fluctuation. Now, let's say I vary those 2 things together. So now this is a 2D phase portrait. Anyone have an idea of what that 2D plot is going to look like based on the 2 1D plots? Mark has an idea. Anyone want to throw anything out? What's going to look like? What is it going to be down in this corner? It's going to be what? Or yeah. Okay, so dark. Let's say dark is no motion, light is motion.
Dark in the bottom.
Dark on here. What about that corner? Probably light. Okay, and then how's the transition going to look? Is it going to be like a nice, gentle blend, or is it going to be something that's going to be more of a step? Based on the fact that these 2 are sharp thresholds.
Squares?
What's that?
2 squares, like a small square, and then it becomes blue.
Yeah. So blue, and then to white. Yeah. Because it's essentially right. Because both of these are, you have, as you're ampling, you're going more and more force, and nothing happens, and then you get this sharp transition. You have a thought? You're making a shape. And that's okay. You think there's going to be this is interesting. So you think there's going to be a transition, kind of this shape transition? Oh, you think this is blue? Okay, but right here below the center line, you think switches to white? Yep. Okay, pretty close. So essentially, we get a almost split. All white in the top, all blue here. What happens here, up for debate. So, but what we notice is that there is a pretty relatively sharp thresholding here, and so you can think of these as slices of this plot, right? So as I go across any of these lines, I go blue, blue, white, white, right? And that's essentially one of these plots, which is flat and kicks up like this. And so we get this pretty distinct, and we did it in simulation as well, where it shows up maybe even crisper, where you get no motion at all until you get across this threshold. And the kind of the interesting thing here is, if you look at, you got some average force. So another question to ask is, if you need to shape change, right, so you want to get out in the white region, how much force do you have to apply as a function of your vibration or your fluctuation? And it's pretty cool to see that, well, as you fluctuate more, you need less and less drive force. Right, and so you can actually drop that drive force down more and more as you fluctuate more. All right, so it could be a hint as to why it's being done in cells, but we don't want to make any claims like that because we're clearly not a cell. Yeah, question?
I'm trying to understand the force fluctuation a little bit. Is that, do you think it's mostly because the static friction is higher than kinetic friction or something? Like you need to almost wiggle and fluidize the...
It's similar to that. It's even simpler than that, potentially, where there's just a force threshold you need to get over to break some connection and move, right? I mean, it's kind of like if you're cracking glass, right? So this is why, like, if you put a little nick in glass, you can get the crack propagation to flow. But you need to get over that threshold of force, right? And so even though our average force, so let's say this is case 1 with no fluctuation, here's our average force. Let's say our kind of critical breaking force is here. Then by fluctuating about this, I'm going to get over that threshold, and then it's going to crack, and then go, and then it's basically an energy flow. It's a downhill slope after that. So it just needs to get itself over that. But if you're kind of thinking of like, if force requires some energy or some power to do, it's more favorable. And I'll talk about power in a minute, but it's more favorable to kind of kick hard and then take a rest. Kick hard, take a rest. Yeah. Yeah. Great question. Yeah.
Force, which parts is that between the two robots, and also the delta F is a spatial frequency, right? Are we accounting for a temporal frequency at all?
Delta F is temporal. Delta F is going to be our temporal frequency. It's the amplitude of the temporal frequency in newtons, let's just say. So it's like how hard. So this is a great question, actually. I'm not varying the temporal frequency. Yeah, that's a great question. So we did that study as well, and more than we can cover here. Yeah. So what I'm focusing on right now is let's fix the frequency and say, I don't know, once a second I'm going to pulse. How big should those pulses be? And another thing I'm not going into is the shape of those pulses, right? So this is some arbitrary thing I drew here. Reality, what we do, we have some distribution of to select from for how big each of those pulses should be, and we looked at all different kinds of distributions and which ones works the best. And it turns out like a very steep bimodal distribution of you basically are always wanting to go up or all the way down, and these little ones in the middle don't help that much, so we kind of get rid of them. And then where are the forces in between? That's a great question. I should have shown that more clearly. This is the force that the gears, basically the torque of the motor on the gears. So when the torque is being applied to each other, this is tangential shear force. How big is that force? And how big are the fluctuations of that force? So it's analogous to the membrane tensions in a cell. Yeah. And this is exactly. So it's basically not doing anything there. All of them are coded with the same, though, because they're dumb. Basically, no cell even knows where it is. We just tell it, go, do this pattern. And they're all doing the exact same pattern. Yeah. Mark, you have a thought?
A detailed question.
Yeah.
So the gears are easily profiled, so you're getting maybe tangent 25 degrees apart also.
Yeah. Which I think is key.
Helpful.
Yeah. In a whole other study on gear shape. Yeah. There's a lot of details we're not going to talk about today, but the gear shape is an interesting one because, if you get them more like a flat tooth interaction, it doesn't work at all because they just lock up. Yeah, no, absolutely. And its tooth size is important too, all these things. Yep. Oh, great questions. All right, so we had that. That was our model, which I'm not going to talk about today, but there's a whole other project which Sung Woo, the postdoc, was mostly working on, is how to model these things and create simulations that to our pleasant surprise, he basically came back a week later or whatever with his simulation, and it was very similar to what the physical cells were doing. So that was awesome. Okay, so we looked at that was shape change, and so now let's do a similar thing with the strength change. So same thing here. These are parameters. Oh, yeah, and this is the drawing to kind of show what that force is representing, right? So it's the force of that gear onto its neighbor. And so then, which anyone who's built a robot probably feels some empathy for these poor little robots that have a 25-pound plate on top of them, but they're very robust little guys. And so the question was, once they're loaded, so they have some strength, can we change that strength? Can we fluidize and soften the collective by controlling these parameters? And so we can, turn them on with some, it's just a picture. Oh, that's such a good video, though. Well, maybe there's one later. Oh, there they go. So we can turn them on, we can soften the thing, and we can drop the weight. So we wanted to look at what this looks like first just with them off. And so this is them, basically their material properties of just an off trio. And we just squashed it in an instrum. And they're very stiff and brittle, up to about 140 newtons on our one little tripod. And then they yield. and then they get into this kind of intermediate state here, as you can see there, and then they collapse fully. So that's what they look like just off, so uncontrolled. And then now we can do the same thing. We can start controlling them by varying this inter-unit force between the gears, and we can soften it a huge amount, right? So this is kind of it's normalized to its max force there, and then we can see how it falls off this way. And similarly, we can do with the vibrations, and so we can drop the stiffness way down with vibrations as well. So with these two control knobs, we're able to both change shape, but also change the strength of the collective. And we can make one of these phase portraits again here. These ones are a little bit less distinct in the diagonal. They're a little bit more just controlled more powerfully with the fluctuation, which is interesting. So especially in the simulation, you see it's almost just a gradient going from left to right. There's a little hint of top to bottom as well. So the driving force matters a little bit, but it's more in the fluctuations. And so this is what I was saying before, is like we built these things, we put them together, and then we get these experiments which we intuitively didn't really, able to predict something like this. So that was a lot of fun to throw these things in there and see what they did. Okay, and then the last little piece on understanding these things, on the small unit ones, this is the 4 to 3 and 4 unit ones, was how does power consumption affected? And so what we did, we hooked these guys up to low power monitors, and you could run them through an intercalation and monitor the power that was required for the robots to do their little thing. And this is a version showing just one, but then we upgraded it to monitor power in all 4, so we could have a sense of the power that was required. And it's pretty interesting to see the savings that we get in terms of power. Now, I will say it is not a reduction in energy, so this is not showing energy, because the ones that are fluctuating tend to take longer. So they end up taking similar energies, but the required power is much lower. So this would be something like, well, you could run these off a much smaller battery, or something like this, where if you're a power limited system, and since biology is often power limited with the flow of ATP, you can actually get into cells. Potentially something like this, the fluctuations could help you reduce your power requirements to do the same motion. And so this was just to show, this is the softening in power changes to do basically those things that I was showing before. So the T1 transition, or to soften enough for to drop the weight. And both of these are showing as you vary fluctuations basically from off to the max that we were doing. Perfect. So just summarize that part. So we looked at the parameters, we looked at the average force, we looked at the amplitude of fluctuation, we looked at the control, and basically we found that it's a very nice knob for controlling shape and strength in these 3 and 4 unit knob systems. But this was our original question, right? We wanted to do things throughout the collective, and we were claiming that people aren't doing things in the center of a collective, and if I only have 3 or 4 units, neither am I. And so our grad student spent a couple more years building a bunch more of these. Is anyone doing collective robotics in here? Good, all right. I would say stay away from it. Once you build a couple of these, I think it gets pretty tiring. And one's always breaking. I think he has like 25, and this is 20, because 5 of them are always in the hospital. So just a little heads up. But anyway, so this is what we put, and then same thing with the light. We're going to polarize it in this direction, so we're going to shine the polarity this way, and then we're going to pause, we're going to shine the polarity this way, and see how the collective behaves. So that's them elongating that way. Then we flash the light this way, and they go this way. And again, note that they have no orientation, right? They're all in different random orientations. They know not where they are. You can rip them apart, throw them together, and they'll just jump right in and start moving with everybody else. This is just to show the simulation similarly. And so the control of the unit has basically 4 regions, and the colors represent opposite direction of that tangential forces. So this would represent a couple of gears turning this way, and then the red represents turning back the other way. And so those are all thrown in to a simulation like this. We give it a kind of a north direction, and we let it do its thing. Or I guess this is elongating this way. Right, so if you let this run long enough, it will actually go fully intercalated into a single line, because that's the kind of the lowest energy state that it can get to. So we looked again at the rearrangements, because that's what we're caring about. And this is, as it's going from this shape to here, you can count changes in topology for each step, and then you can plot that. And basically, it correlates with elongation, which makes sense. So as you get more rearrangements, you get a more elongated shape. Also, we can compare rearrangements to our fluctuations. So again, the more we fluctuate, this is for 30 seconds, so per unit time, the more you fluctuate, the more rearrangements you get. And then similarly, as you add more fluctuations, so each line is greater fluctuation, you get more rapid shape change in across this time interval. And then, so that was shape change. We do a similar thing for strength change. So now we put weight on top of the full collective, and we can turn them on, and they're going to soften and drop our weight on command. And similarly, in the simulation, we can do something where we turn them on, and we can start softening the whole thing, which is starting to look rather cell-like compared to my original video. And then at the collective scale, we can also do some material testing. So this is the whole collective of 20, and it's basically a brittle material. This was a sad test to do for my grad student, but it does fracture at some point. And then once you turn on, this is basically full fluctuations. You get this very visco plastic material that essentially just flows. And once you release the load, it doesn't come back at all, right? So it's purely deformed. And similarly, you can take this and run it for a bunch of different fluctuations. This is basically showing none and full, but you can do the same thing over and over again and get a yield force for each one. And we can see that we can drop the yield force to almost nothing with those fluctuations. So basically fluidize the material like Terminator. We can do spatial control as well. It's a little hard to do in 20, to be honest. So you have to, bear with me here a little bit and believe me that it's happening. But we're not going to fluctuate the right side. We're going to fluctuate the left side. And those right ones basically, so they're on, but they're not fluctuating. So they don't really move. Whereas these ones, this side, are starting to do their elongation behavior over here. And I think this would be more dramatic if we had twice as many robots, but then my grad student would quit, so that's not going to happen. And then we do similar things on weights. And so we have, we're going to leave these ones not fluctuating, and we're going to fluctuate the far side. So we can maintain strength on this side, and we can soften that side. And so we can do spatiotemporal control of shape and strength. And that's those are the main two parts of what the research was, and then we had some fun with it. And so I'll finish up with just showing a few of the demos that we've done with this material, with that collective of 20 robots. And so, again, these are kind of simple behaviors, and I'll leave it to all your wonderful imaginations to think of if I had 1 million of these and it was 3D and they were micron scale, what could you do? So this is the first step towards that. So the first one is structure forming. So we wanted to do something where they were flowing, but then able to support the load in some way. So we have kind of these two pillars, and they're gonna flow up towards one another, and the light's kind of on one, and then the other at this kind of diagonal. So he's kind of going back and forth, and then he's able to bridge them and then push. And I think this is kilograms. So he's up at about 4 kilograms of force. So they're quite strong. He's able to make quite a strong structure. Once he turns it back off, it solidifies again. We can do kind of a healing thing, which after you've seen these, it would make sense. But imagine you had Terminator, and he's got his hole in him, and you can now turn them on and fluctuate, and they're going to flow into this space, and we can get kind of back to a tight packed, very strong material, essentially instantly. Right? There's no some of the self-healing things that require molecules to come back together have a longer time constant. this one, okay, this one's a bit of a stretch. But imagine you had a wall made out of this, and you wanted to like hang up a nail in the wall. You just like, tell this spot to soften, and you just gently place the nail in the wall, and it would harden again. Cool idea. We have some work on the implementation. So we have this big like foam nail we're gonna stick into the wall made out of 20 robots. So, but yeah, it's kind of interesting. So right now we're showing it going in, and then we turn them off, and so now it's solid again. And you can show you can bear a load with it, which like I said, use your wonderful imaginations with that one. But I think that was a kind of a fun one. And then, of course, we have to do some manipulation, or I wouldn't be Mark's student. And so this is picking up these two different shapes. The point here is that we can make, take the shape of one thing to reach down into kind of this narrow gap, and we'll move it. And then we can change into a bigger manipulator to move that larger egg, or whatever it is. And so we come over, and we're just kind of moving this around 2D. So it kind of reaches in there. And then we're able to basically move it like a rigid body, and then drop this thing off, come over here, and then we can flow again, and then we'll get, we get a bigger shape to drop it off over here. And you might wonder why it has such a weird background on it. That's glass microbeads to get really low friction, so we can slide these things around, which was make sure we didn't get those on the floor. I don't know if anyone's walked on glass microbeads before, but it's not a good thing. And the last couple ones here, so this is kind of like a wrench type demo. So imagine this is a triangular nut that you need to turn, and these are going to flow around it, and then we're going to, again, manipulate the collective. So, it can form, we're going to flow it up around the nut, and then you're able to actually just push the whole thing. You can imagine, again, if we had the higher resolution, you can make a wrench that could wrap around any nut you wanted. And I think the last one is a little manipulation demo, moving a little block around. And so these little guys turn on. I think this is kind of the cutest one. They look like a little team here trying to figure out how to get this thing in there. And they're not always heading in the right direction. And then they get it, and then they didn't quite get it, and then they come back. Come on, yay! That one always makes me happy. So I'll wrap up now, as we have a minute for questions. But we looked at the design of these robots. We looked at how they behaved in the collective. And then we looked at some demos. And what I started with, and I hope I've somewhat convinced you of, is that these topological rearrangements are interesting, especially when we're doing them throughout the collective, right? And so the whole collective can move and change shapes. And this is maybe a very first step moving towards this programmable matter vision that we see in the tissue and the science fiction. So with that, I'll take any other questions, and thank you guys.
Super cool. 3D?
Yeah, no, that's a great question. So I mean, the cells do it in 3D, right? It's interesting because most of what our visualizations of the cell is 2D, and so that's kind of where we start. But I don't think there's anything inherently, because the physics works in the cells, and it's the physics we're using of this motion, we don't yet see a huge problem. We need to figure out how to do it, of course. So it's not like I have that in my next slide, but no, that's obviously the next thing to think about. Yeah.
This is a sort of research philosophy thing. What additional value did you find? What more did you learn by making physical robots to demonstrate these ideas versus doing everything in simulation?
Yeah,
You're a graduate student that you invoked many times would have been happier probably.
If we've done this all in sim. Yeah, no, that's a great question. So I think a person who we've worked a lot with and some on this stuff, Dan Goldman at Georgia Tech, I don't know if you know him, he's big into what he calls robophysical models. And so this is essentially a robophysical. Oh, I say there's two branches of this work. One is a purely engineering drive, which is robotic drive of, can we make this material, right? And so for that, a simulated material is less useful than a real material. So I'll say that's the first answer. The second, though, is what do we learn that's not in simulation? So his big pitch, and he's written some nice articles about this, is that there's always something wrong with your simulation. Nothing can be perfect. And there's actually some interesting simulations of those previous robots I showed that can do this behavior throughout. And then in reality, that you just can't because of jamming and things like this. They just didn't model the friction correctly. And so in my mind, yeah, it's a simulation, but maybe just with that extra little level of reality to it. Friction is really, really messy. Yeah, like Mark was saying with the shape of the gears and stuff like that. It's really tricky. Thanks, Steve. A couple other questions here, yeah.
I was curious in the last demo that you showed how they were controlled. Like, was it autonomously figuring out how to solve
Great question. The grad student. He called it, human in the loop control. That's one of his favorite. So I think that's another. Allison asked about 3D. I think that's another great next step is the controller, especially as you get more of these. And so he basically has a light with a polarized filter on it, and he's just moving it around in 2D and rotation. So he has just those degrees of freedom. So presumably he could have recorded it himself and then replayed it with a robot. But that's how the controller works. It's essentially just a light. I think he turns it on and off, so that's his other degree of freedom. Yeah.
Okay, so just one light moving around and it does the
Yeah.
Okay.
And he, it's not always covering all of them, right? I think he's able to maybe partly shades it as well. So he's basically you can focus it, you can expand it, and rotate it, and move it. Yeah. No, that was all behind the scenes. That was not clear at all. Good question.
Okay.
Another one over here, yeah. Okay.
Another interesting extension of cells that comes to mind is the fact that cells are able to communicate with their neighbors. Do you think there could be any added utility to doing that with these robots?
Yeah, that's a great question. I think the control side of this is really interesting, and the distributed computation, things like that. Right now, these are basically as dumb as you can imagine to get the system working. And nearest neighbor communication, Kilobots does that. So the one I showed that we're making the stars, that's how they talk. So they all know, they can talk to their neighbor, and then there's certain ones that know global position in that. So that's how they make the stars. So they have like special ones that know where they are. Then they basically communicate through each other to do stuff like this. So you could imagine a scheme like that as well. Yeah, no, great question. Yeah.
I had two questions. The first one, the metaphor for the I'm sorry, the word is morphogenesis.
Yeah, morphogenesis. Yeah.
Morphogenesis.
Yeah.
I guess since that happens on such a smaller scale, and particularly for cells where they have like kind of polarized sort of membranes with the phospholipid membranes, I guess what makes it so compelling on such a larger scale?
Yeah, so that's a great question. I didn't make that clear at all. So in my mind, this is our first step, and then the goal is to scale it down. Yeah. Maybe not quite cell scale, but sub-millimeter, I think starts getting interesting. Like once it becomes into Allison's point 3D as well, and the vision is like those movies I showed at the beginning. And even the Big Hero 6, they're kind of this big scale, and it's still interesting. So I think 3D and kind of that scale, you can do some interesting things. Does that make sense?
Yeah, I guess the distinguishing part from swarming.
Yeah.
Even though a lot of them do go in the perimeters.
Yeah.
Also, this is not my area of expertise. I'm going off of like ants documentaries where the ants go over each other too, and like they're also different.
No, exactly. So swarming, which is what Kilobots I think is a little more inspired by, right? Is more swarm behaviors. And so what I would say, another way I like thinking of this is it's a little bit like injection molding or like materials processing. So imagine if you have like a metal and you want to make it into a spoon, you basically are rearranging the molecules, but you do it with very large external forces and heat. And this is, in a way, allowing you to do material processing internally. So the energy is coming from each of the units. So imagine now, instead of doing, basically at design time, you have to decide what your spoon looks like. Now you have it, and it can do any shape afterwards from its inside out.
Sorry,
Yeah.
the radial light thing is cool. What are the limitations in terms of like, I guess, resolution or like how much control you have over
Yeah, no, that's a great question. I mean, basically, you could imagine a system that's basically a projector, like to that level, right, where each one is getting a signal from each one. Yeah. So you should be able, I mean, light's nice in that regard, is that you get very high resolution with light. Yeah.
Would you consider other sensing mechanisms?
Yeah, that's a great question, because again, like my example of something where you have like a spoon, like, I don't know, what would you do? You throw it into like your light box to recreate it into a new shape, and especially once you go to 3D, light's going to be trickier. So I think this one was convenient for 2D, for what we were doing. I would not say it's the only way, and maybe not the best way. Question here?
Yeah, interesting talk. When you think about cells themselves, a lot of the time the impetus comes from two cells separating and then the rest kind of rearranging, right? Would there be any interest in also in favor of saving your grad students many hours, but like on making a lot of these passive and having just a few like active elements in the middle of them and seeing like whether you can get a bigger swarm and essentially control parts of the swarm by controlling only individual elements.
Yes, he did that. I didn't point it out, but there was some sleight of hand. In some of those demos, he actually had dummies, he calls them, where they look just like the other ones, but they're not doing anything. And so that's a great idea. So you don't need 100% active. Yeah, that's a great point. Yeah, and it would be an interesting study, which we haven't done yet, is what % active do you need to do certain tasks in? And that's an interesting question. Yeah. We have, I guess, okay, one more, and then, okay, one more here, one more. Okay, why don't we start here since, yeah.
These guys are sticking together with magnets.
Yes, yeah.
You guys considered, there's like a hypothesis in morphogenesis, it's called the differential adhesion hypothesis. I was wondering if you guys have considered sort of varying the
Absolutely.
attraction
Yeah, absolutely.
of these guys to sort of see if they can arrange themselves based on just like your simulated surface adhesion.
Yeah, no, absolutely. And so that's a whole other knob to turn is the adhesion. And we basically said, we're just going to leave the adhesion fixed. For this set of experiments, let's look at the forces. But yeah, absolutely. So in cells, adhesion's changing dynamically as well. So that could be another knob, electromagnet, something like this. You could change that. No, that's a very cool idea. Awesome. And I'll talk later, so you can ask me then. Okay.
Thank you so much.